Hello friends, this is again Dr. S. D. Raut from Nagesh Karasgi, Orchid College of Engineering and Technology, Solapur, Maharashtra. Today we'll begin with the next unit in sequence, unit number 2, processes and CPU scheduling. Now these are the various concepts that will be covered one after another in detail in this unit. Let's begin with the first point in the unit, the process concepts. Now, how a process is defined? A process is simply a program in execution. Remember that we store programs on hard disk. Something of their, some of them we might create shortcuts on the desktop and we double click a shortcut. What is stored on the hard disk is a program. When we double click it, execution of the program begins, and the program, when it gets into execution, it is known as a process. Okay, process is also called a job. Well, as I said, program is an executable file stored on the hard disk or the secondary disk. Usually you might have studied that a process have 4 segments: code or data text segment, then data segment, then is the stack segment. The arrow indicates that stack increases and decreases from the top, and there is what is called as a free or heap segment, which is made available to the program or to the process in execution. A process in its lifetime goes through a number of various states. These are: when we double click a program, a process is created. At that time the process has the status new. So in this state the process is being created. After creation, the process may start executing after allocation of CPU. Now, so instructions of the program or the process may start getting executed, and in this case the state of the process is said to be running. In execution, in the running state, a process may demand something which is currently not available, and it has to wait for it, or it might initiate a process which is going to take a longer amount of time, and for executing that process it doesn't need CPU. In both cases the process goes in waiting state. So in waiting state, process is waiting for some event like input output or reception of a signal or reception of a message from another process. There are n number of reasons why a process may be in waiting state. Another state of a process is ready. A process is said to be in ready state when it has all other resources except CPU. So it is waiting just for the CPU allocation. The moment CPU is allocated, the execution of the process begins. That state is called as ready state. Terminated. Obviously, when process finishes its execution, it is terminated. Now these states are shown here in the diagram. When a process is created, it goes into the new state. Then after creation it is transferred to another state called as ready state. Remember that this is very obvious because nobody knows, including process, what it is going to need for execution. So a newly created process gets into the ready state. Now from the ready state, the process might get allocation of CPU, and then the state of the process becomes now running. The new process is created, pushed into the ready state. From the ready state, it is when CPU is allocated to it, it gets into a running state. Now from running state, there are a number of transitions possible. Number one, when the time slice for which CPU has been allocated to the process completes, it is brought back from running to the ready state. So here again, it hasn't asked anything else in the time slice of the CPU except CPU time. But CPU time is over, so it is brought back to the ready state. Another possible transition from running, it might demand something which is currently not available. It might have to wait for an event to occur. For example, in running state, it might ask for some input-output operation which is going to take a longer amount of time. And unless and until that I/O is complete, it, even though it has CPU access, it cannot proceed. So better thing is take away the CPU from such a process, put it into the waiting state. When the I/O is complete, something else will be done with the process. Or it might be waiting for a message from another process in the system. It goes into the waiting state. There are a number of reasons why a process gets from running to waiting. We'll be going in details of all these as we proceed. And from running, there is third possibility that the process might terminate. The process in running state might find out itself that, well, it has done all the job that was assigned to it, and it can now exit smoothly out of the system. Remember, I am saying smoothly out of the system. It might also happen that the process might be terminated by another process, but we'll get into those details later. But from running, the process may be terminated. Okay, I just repeat for once. A newly created process gets into the ready list. When CPU is allocated, gets into the running state. From running, three possibilities. When time slice completes, it comes back to ready state. When it completes its execution, it is terminated. And when it demands something which is currently not available, it is pushed into the waiting state. In waiting state, a process is waiting for something to occur. For example, an interrupt or event, whatever it is. And when that event occurs, obviously, process then want is only CPU. So after that, the process state is changed from waiting to ready, and the whole process continues. But these are the typical 5 states through which a process goes through in its lifetime. Now there is something called as process control block, popularly called as PCB. What for it is used? Operating system represents each process by a process control block. In other words, talking in programming language, there is a struct like in C which is called as a PCB. It's nothing but a data structure. Okay. The data structure contains information as below. Number one, it contains state of the process. So state of the process may be new, ready, running, waiting, or terminated. Typically after termination, the memory allocated to the process also is taken back and the PCB is removed from the system information. But yes, one of the 5 states is recorded in the process state. Program counter. This indicates address of next instruction to be executed. Popularly, we already know while learning to the microprocessors. CPU registers. like accumulator contents, index registers, stack pointers, general purpose registers of the chip, and any conditional information. On interrupt or process switch, this information along with PC is stored and forms the context of process or forms process context. We'll be going afterwards in details process context and process switch as we proceed, not far away from now. Okay. There are other fields that goes in the PCBR. CPU scheduling information. You recall, different processes in a system have different priorities. So what is the priority of the current this process? To whom this PCB belongs? That is recorded here. It might have a different, based on priority, it might have a different scheduling queue. So pointers to its scheduling queue and any other scheduling parameter that goes for the process. As we proceed, we'll be dealing in detail with scheduling parameters either in this unit or might be in the next unit. Memory management information about the process. So value of base and limit registers, page table, etc. etc. Just at this moment, just remember that memory management information goes into the PCB. We'll be dealing with memory management in absolutely two details in unit number 6 as we proceed. Accounting information. So information like amount of CPU, time that has been used, the real time it has used, time limits, account numbers, process numbers, etc. etc. This is very similar to our service provider records about our calls made by our cell. Then IO status information. This information includes list of IO devices allocated to process, list of open files on behalf of this process, etc. etc. So some other information goes which is related with input output. So that information also goes into PCB. This is a typical data structure used for a PCB. State of the process, process number, or program ID or process ID, PID popularly called as program counter and stuff like that which we have discussed just now. Scheduling of a process. Objective of process scheduling is to increase maximum usage of CPU. Now the question might be asked, why there is this major concentration on usage of CPU, why not other resources of the system like hard disk and keyboard and mouse and other stuff or monitor, etc. etc. Do remember that out of all these things, CPU is the costliest resource of the system. Hence, efficient utilization of CPU is always the target for any scheduler. Now there should be at least one process running at all times. That is what is the target. So keep the CPU busy as much as possible. Okay. Time sharing system. In case of multi-processing systems, so where more than one processes are running, CPU time is shared among number of processes. So CPU gets shared as we have seen in the previous example from running to ready back because the CPU time burst has been complete and now another process gets scheduled onto the CPU. So CPU time is shared among number of processes. This allows user to interact with each program while it's running. Process scheduler selects a process from available processes from ready list for program execution on the CPU to run for a time slice. Always remember that process state diagram. Okay, we saw a ready state. There might be more than one processes in the ready list or ready state, and one of them is allocated CPU at a time. Which one to allocate? That job is done by a scheduler which is called as process scheduler. Now here is an example showing CPU switch from process to process. This line indicates is there for the process. It indicates the status as executing or idle or executing. This is for process P0, this is for process P1. In the mid is what shown is the actions taken by operating system. Now we start from the top. Process P0 is under execution. Needless to remind you, concentrate on the mouse movements. Here P0 process is in execution state, that is in running. Then after certain time period, its time slice has completed. So what needs to be done is the process P0 need to be brought from running to ready, and another process from ready should be scheduled onto the CPU. So another process is transferred from ready to running condition. Now what happens is, once an interrupt is or a system call indicates that time slice for P0 has completed, operating system comes into play. It saves state information of PCB0. PCB0 is the PCB of process 0. So it saves all information that might be necessary when we want to restart process 0 after some time. So it saves state into PCB of P0. Similarly, it has saved already state of all information about P1 in PCB1. So now what it does is it reloads that information for process 1 from PCB onto the CPU, and then execution of process 1 begins. Now for this time period, P1 is in running or executing state. Now at this moment of time, the time slice allotted to P1 is complete. Now P1 is to be taken out. The only other process that is waiting for CPU is P0 right now. So it is scheduled onto the CPU. That means now P0 becomes into running state. Exactly reverse of these two steps are being done here. This is how basically happens in a switch of a process. Scheduling queues. I said there might be more than one process in the ready list, right? How these processes are maintained? All these processes in a particular state are kept in a list, and if the list contains all processes in the ready state, then the queue or the list is called as ready queue or ready list. This typically contains processes in main memory and are ready to execute, as we have seen already. This is usually a singly linked list of PCBs of all processes which are in ready state. Ready queue header contains pointers to the first and final PCB in queue. The ready queue header contains two pointers, one to the first in sequence and another to the last in sequence. There is another queue called as device queue. A system may have more than one devices, so for every devices it maintains a separate queue for every device. And the processes waiting for the device are kept in this list. Now this is the diagram. The ready queue and various I/O device queues are shown here. Let's begin from here. This is the ready queue. This is a singly linked list of all PCBs which are in the all processes which are in ready state. The PCBs contain information what we have discussed earlier. But importantly, the ready queue contains, the queue header contains two pointers. One pointer to the first in sequence PCB and tail pointer to the last in the list PCB. The usage becomes later clear when a process is scheduled. This goes out of the ready queue into the running state, might come back, but when it comes back, it is inserted at the end. So processes are taken out using head and pushed into using tail. There are other devices called as magnetic tapes. Nowadays nobody uses those magnetic tapes, but they are shown here and just for the sake of existence. Now we do find disk, and a computer may have more than one hard disk. In that case, the disk unit 0, disk unit 1, disk unit 2, etc. will be numbered. Now, all processes which wish to do I/O operation with disk unit 0, obviously, if one process is doing the I/O with the hard disk, the other process has to wait until the process completes its I/O with disk unit 0. So this is the list of all processes which are waiting for access to disk unit 0. Okay? Again the same thing, this header contains two pointers, one to the top, another to the last. This is again singly linked list. There might be another device called as terminal unit 0, might be shared among number of processes. When one process is using it, another process has to wait. Now typically here, peculiarly, there is only one PCB in this list. So head and tail both are pointing to the same PCB. Now this is queuing diagram representation of process scheduling. It's like redrawing the diagram of process state. But let's see it. When a process is created, it is in new state. From new state, it is brought to the ready state, goes into the queue of ready processes. In other words, it goes into the ready queue. From the ready queue, it might get scheduled onto the CPU. Now from CPU in execution, there might be a number of possibilities are there. One, it might say that I am done, goes out of the system. In other words, the program may be, the process may be terminated for natural cause or otherwise. Or while running, the process may demand some I/O, that is, it puts a I/O request. In that case, obviously it has to wait. Since it has to wait, upon receipt of I/O request, the process goes into the I/O queue. When its number comes, it completes its I/O, and when it completes its I/O, goes back to the ready queue. Okay. Second possibility, when the process is in running state, it might not demand anything else, but what might happen is its time slice of the CPU is complete. That is, time slice is expired. So process may be brought from running to the ready again back. This transition we already seen. The third possibility, let me go to the fourth one first. CPU, it might now demand something, or before it proceeds, it has to wait for certain thing to occur. And occurrence of that event will be communicated to this process through an interrupt. So it is as good as to say that from running, it might go into a waiting state for an interrupt. Okay? It is waiting for an event other than IO to occur. For example, it is waiting for a message from another process. Something like that. Okay. Now when that interrupt comes for which it is waiting, the interrupt is received, processed, and now process has to wait for nothing else than CPU, so it goes into the ready queue. Okay. Now the fourth transition is a bit interesting. A process can create another process in a system. A process can create another process. That is called as forking a child, or a process fork a child. It creates another child. Now because of certain conditions, the parent process which has created a child process has to wait until its child completes its execution. We'll be going in details as we proceed, but currently remember that a process has created another process and it has to wait until the child completes its execution. So main post process or parent process goes into the waiting state, waits for child execution. When the child execution completes, the parent process goes back to the ready queue. Okay. Schedulers. So basically, who does the job of picking a particular process to schedule onto the CPU? Or if there are more than one processes in the waiting list, who does the job of picking the right process from the waiting and pushing them into the ready list? All these tasks are done by what is called as schedulers. A process migrates among various queues in its lifetime, obviously. So for scheduling purpose, operating system selects processes from these queues. The selection process is carried out by appropriate schedulers. And there are three types of schedulers for three types of situations. 1. Short term. 2. Medium term. 3. Long term. Let's go into details of these different schedulers. First, short term scheduler. The scheduler selects a process from ready list for CPU allocation for a very small time period. So, importantly, short-term scheduler is selecting a job from ready list to allocate CPU. So for transition of a process from ready to running or running to ready is the responsibility of short-term scheduler. Now we also say that for certain time amount, CPU is allocated to a process. Now that time amount per process of CPU is called as CPU burst, which is typically a very small time period of around say 100 milliseconds. So after every max 100 milliseconds, the algorithm will be called again and again and again. Every time it is selecting different process from the ready list. So processes from ready list are selected in round robin fashion. So one after another, one after another. When a process completes, it goes back into the tail of the queue, and when its number arrives, it might become head and then get scheduled onto the CPU. So it's a round robin fashion. So since CPU bus is too small, what is happening? It has two effects. One, the algorithm itself should not take more amount of time. Go back few slides. Now observe here. This is the amount of time for which the process is actually executing, and we can say that time from which earlier process has stopped executing till the time at which new process has taken up is idle time. In fact, idle from process point of view, also from operating system point of view, because the operating system is doing job of saving state of the earlier process and reloading it, and this job is done by the short term scheduler. Now if the execution time is less, it is normal expectation that the algorithm time of execution should also be very less. So the algorithm itself should not take longer amount of time. In other words, this has to be one of the most efficient algorithm of operating system. Second, frequency of scheduler invocation is high. So after every 100 milliseconds, the short-term scheduler is called upon. Now because of these two features, you can say the scheduler is called as short-term. First reason, duration of it is less, is short, and the frequency or the time period between two calls is again short. So this is called as short-term scheduler. Next is medium-term scheduler. Now consider a situation. All RAM is allocated to existing processes, few of which are in waiting state for considerable time period. So there are more than one processes. Every process when created has demanded some primary memory, that is RAM. It has been allocated. Now system does not have any extra memory available. Whatever it had distributed among all existing processes. Also is the state that few of them are in waiting state for considerable amount of time. Now what is happening is a new process is to be created. Obviously, whenever a new process is created, RAM should be allocated to it. But then there is no RAM. It has been consumed by all existing processes. Now the question is, the RAM has been allocated to a process, but it is not using it because the process is in waiting state. In waiting state, a process is waiting for some other thing. It has RAM, it has chip. Okay. So now the question is, why keep the allocated RAM with the process which is currently in waiting state and hold back unnecessarily a new process and tell him that no boss, we cannot create you because currently RAM is not available. Not a good answer, right? So what option is preferred by the designers is a process which is already allocated RAM and is in waiting state, typically for a considerable amount of time. How about shifting such processes temporarily to the secondary, thereby making some RAM free, and then allocating this newly freed RAM to the new process, so that a new process also can begin its execution. Alright. This process of taking away RAM from an allocated and waiting process, storing all information or RAM contents of that process onto the secondary, and reallocating the newly freed RAM to a new process or another process, whatever may be the case, is called as the process has been swapped out. Right? The process which goes out of the RAM onto the secondary is said to be swapped out process. Obviously, after some time, when the event for which the process was waiting occurs, RAM is available, the process which was swapped out will be brought from secondary to primary, and that is called as swapping in. So swapping out, swapping in. When the event for which the processes are waiting occurs, these swapped out processes are swapped in. They are brought from secondary to the primary. Now all this job is done by a scheduler, and remember that the frequency of calling such algorithms may be less, may not be the least, but may be less. However, the time it will take for taking out a process from RAM, storing it onto the secondary, then loading state of another new process into that RAM, or allocating the RAM to another process might take a bit of longer time as compared with short-term scheduler. So this is called as medium-term scheduler. Now third, obviously, okay, before we go for that, this is what happens. From ready queue, process goes into the CPU, might go into the IO waiting queue. When IO completes, goes back to the ready queue, or if it is waiting for longer amount of time, the process may be swapped out onto the secondary, and when the event occurs, it might be swapped in. The process is called as swap out a process, swap in a process. Okay. The third type of scheduler, long-term scheduler. Earlier two schedulers typically are used for interactive processes. In unit number 1, we have seen non-interactive processes, which are typically submitted in a batch, in a group, where the user is not in front of the system for interactions. Program is taken, loaded, executed, output is generated, stored, and next process is taken. So that is what happens in batch. Now, scheduler for these is the long-term scheduler. These batch processes are spooled onto the secondary for later execution, not immediate execution. That means their priority for execution, putting them, allocating system resources is less. Batch processes are selected on availability of required resources like RAM, CPU, IO devices, etc. etc. Long-term scheduler does this job of selection. Usually batch processes are described into one of the three categories. This is interesting, and remember now this, and then you will understand why a long-term scheduler is needed and why a good mix of batch is also needed. There are certain processes which are said to be CPU bound processes. Typicality of these processes: more time is used for computation than generating IO request. So processes which fall in this category typically require very less IO, might require very lesser amount of memory, but they heavily demand CPU time, because what they are typically doing are the statistical computations, something that is needed in scientific programs. And for statistical computations, what they need most is CPU, right? Another category of the processes is IO bound. Feature of this spends more of its time doing IO than it spends doing computations. So majority of the time it does IO. For example, a messaging system. A messaging system is meant for IO, input output. Transfers messages from one process to another process, one system to another system. It needs CPU for very less amount of time, but takes longer amount for actually performing IO. Third kind of or category of processes is memory bound. Now these are the processes which will say might require less CPU, I might require less IO, but I need huge amount of RAM. So these processes are data intensive processes. For example, database applications always need or work with huge data, and they might require RAM in gigabytes or terabytes. So their memory RAM requirement is higher. Long-term scheduler carefully selects good process mix so that all three resources are used properly. So what does long-term scheduler does? It checks what is the state of these three resources. Whether system is currently underutilized for CPU or IO or memory. If it is CPU is not being kept busy by existing processes, then what it does is it selects a process from batch which is CPU bound. So this CPU bound process from batch will see that the CPU is being kept busy. Same is the case for IO and same is the case for memory. Operations on processes. This we have seen, right? Process creation, process termination. But now we are getting into details of this. The first operation is process creation, and then we'll discuss process termination. Process creation. A process creates another process via create process system call. So process is creating another process, and the system call that is used is create process call. The process which creates another process is called as parent process, and the process that has been created by the parent process is called as child process. Every process is assigned a unique identifier called as PID, the process identifier. P for process, ID for identifier. So every process has got a unique PID, which is typically an integer number. Most of the operating system follow this strategy. Importantly, on boot, operating system creates system process with PID equal to 0, which is the parent process for any process later created in the system. So this is parent of parent, all parents. Now here is an example, a tree of processes on a typical Solaris system. Well, I'm not interested in going in all details. These are typically very related with specifically to Solaris system. I would like to draw your attention, when a system boots, this process is created by the operating system first, and this is parent of all. Okay. Importantly, for all user type process creations, this SHED creates another process with PID equal to 1, and the name of the process is child process is init, and init is the process parent process for all pro user created processes. These are processes that are needed for operating system to run. Got it? Details of these are mentioned here. As I said, too importantly, process at the top of tree is SCHED with PID equal to 0, and init is the root parent process for all user processes. So any user processes, the root is init. Okay? If you have time, go through all these things. Might help you. A process needs certain resources like CPU, time, memory, files, IO devices, etc. Now when a child process is created, one of the two things may happen. In lifetime of a process, the process may need different resources from the system. Now child process is created, and one of the two things might happen about the resources for this child process. Number one, the child process is able to obtain resources directly from OS. So the child process is a complete process. There is no relation between child and parent, and child becomes a complete process. Parent is a complete process, and both are competing for now equally for system resources. So a child becomes parent now. Second possibility, the child remains as child. So the child process may have to share parents' resources. So this bonding is fixed. Child remains child of the parent, and whatever parent has, all those resources only are available to the child process. The child is restricted to share parents' resources, not given explicitly new additional resources as demanded by it. If it needs, it has to demand to its parent, and operating system will allocate those resources to the parent process. Now this is done to avoid system resources getting overloaded. Obviously, by keeping the bonding between child and parent and asking them to share the resources, operating system is trying to reduce number of processes which are competing for the system resources. There are two execution possibilities for parent process might occur. Parent continues to execute concurrently along with its children. This is analogous to previous one, number one, where child becomes parent and starts working as a separate complete process. So in that case, the parent and child can continue their execution simultaneously. Second possibility, where child is sharing, child remains child. In that case, parent has to wait until child completes its execution. So parent is suspended, child proceeds, child completes its execution, and then an interrupt is generated for the parent, and then parent re-begins its execution. So that is the second possibility. Similarly, there are two possibilities about address space of new process. A child process is duplicate of parent process, has same program and data as parent, or a child process has a new program loaded into it. So child remains child, child becomes a complete process in it. Remember that the order is reversed here. Here the child is remaining child, here the child is becoming a complete process. And when it remains, a child remains a child, it shares resources of the parent process. When child is complete program in itself, a new code, new program is loaded for it. The same is shown here, where process creation is in force system call in Unix system. So parent from here executes fork. With fork it creates a child process. However, parent remains there, but parent has gone into wait state. Child comes into play, is created. With exec command, the execution of child begins. After some time, the child might complete its processing, might generate an interrupt indicating waiting parent that look, I am done, and now parent might resume afterwards. Alright, simple enough. The flip side of process creation, process termination. A process may be terminated in two different conditions. One, self-termination. The process has finished its execution by executing its final statement and ask operating system to delete it by using exit system call. So the process has done whatever it wanted to do in the system without any hazard. It's completed. Now on itself it is telling the operating system that look, I'm complete, I'm done, I'm exiting. Please terminate me. And it tells so to the operating system by executing a system called as exit. Process may return status value. For example, in C, 0 for successful completion, else an error code is written by any process. Operating system obviously reclaims all resources of the process like physical and virtual memory, open files, IO buffers, etc. etc. All the system resources which are assigned, which are allocated to this process in its lifetime. Second reason why a process is getting terminated, due to parent termination. A parent process may terminate its child process abort in one of the following conditions. So parent is aborting child process or terminating child process. The child has executed its usage of the allocated resources. So from parent process point of view, child process has done whatever it was and it is done away with the allocated resources. Or the task assigned to the child is no longer now needed. So in that case also parent may feel that I don't need this child process to exist in the system and unnecessarily compete for the system resources. Third, the parent process is exiting by terminate process in Windows 32. In Windows 32, when a parent exits, all its child processes must exit. This must exit is done by the system with a forceful termination of all child processes. Alright? The concept, threads. About threads you will learn more and more in Java also. But for now remember, a thread is a lightweight process. Typically a thread is called as a lightweight process. So it's a process but lightweight. Typically a child process. Smallest sequence of program instructions schedulable independently by a scheduler. Smallest one. Lifetime also very less. Thread implementation differs between operating system, but in most cases it is a component of a process. So it comes as a parasite of a process. Doesn't exist on its own. Multiple threads can exist within one process. If you are a serious Java programmer, you will understand that one program can create multiple threads. So multiple threads can exist within one process, executing concurrently and sharing resources such as memory. Think of threads as child processes and the things will become easy to understand. In particular, the threads of a process share its executable code and the values of its variables at any given time. So they are sharing everything, code and data all together. Okay? Yeah. Now let's move on to the next bit in the unit 2.5, inter-process communication. This inter-process communication is popularly called as IPC. IPC provides a communication mechanism for creating for cooperating processes. There are two standard mechanisms available for IPC. One, shared memory. Two, message passing. Let's see what these are. Now, the diagram towards left is for shared memory. Look what is happening. There is process A, process B, there is kernel of operating system. Now A is here, has been allocated this part of the RAM, B has been allocated this part of the RAM, and now what they are saying is this part of the RAM or the memory is being shared by process A and B. Alright. Also the arrows indicate that in this shared part, process A is pushing data, and this arrow indicates that process B is reading data from the shared memory. The reverse can be true. It can also be true that both processes are reading, both processes are writing. But importantly, this is the part of the memory which is being shared by these two processes here. That's why this communication mode is called as shared memory. Message passing, which is the other mode of communication. Every process has got their own memory. Part of their own memory they separate out and they are calling it as mailbox. Okay. And in this mailbox, messages can come in or messages can go out. Okay, we'll get into details of both these communication modes one after another in detail. Let's move on. Shared memory systems. Recall this diagram. If necessary, draw it on a piece of paper. Now, shared memory systems requires communicating processes to establish a region in shared memory, typically in address space of a process. Maybe, may not be. But yes, there is a region which is established by these processes and named as shared memory. Other processes sharing this region attaches themselves, thereby saying that we are the participants in the communication using shared memory. Communicating processes can exchange information by reading or writing in this shared memory. Form of data, location, format, etc. are decided by the communicating processes. This is important because operating system is not playing any role in it, and hence everything is decided by the sharing processes. The shared memory is not under control of operating systems. Operating system doesn't have to do anything with this shared memory. Communicating processes are responsible for maintaining concurrency control. So, shared memory is there, area which is being shared, it becomes critical section, and then all the stuff that is concerned with the critical section will come into play, which calls for concurrency control. This is a typical producer-consumer problem. Producer produces items that are consumed by consumer. Normal definition of producer and consumer. The producer stores produced items in shared memory, which are then picked by consumer to consume. And shared memory is referred as buffer, which can be finite, which is practically also called as bounded, or it can be infinite, which is called as unbounded. Of course, unbounded shared memory exists only theoretically. Example of producer-consumer problem: client server. For example, web server which produces HTML file and images, and client is web browser which is consuming these HTML files and images. Consuming in the sense made available to the readers for reading purpose. Compiler is another example. Assembler produces, recall compilation process of a program. Assembler produces assembly code which becomes input to object model creator. Object model creator consumes assembly code and produces object model which becomes input to linker, which consumes assembly code links with library and produces executable code. Right? So assembler is producer, object model creator is consumer. In the next step, object model creator is producer and linker is consumer. Another example is Facebook. Second method or mode of communication is message passing systems. Operating system provides this mechanism. Now importantly, this is under control of operating system. There is no shared memory. Every process uses its own address space, which it declares as a mailbox or buffer. Now, I would strongly recommend you recall WhatsApp. Almost everybody is now habitual of using WhatsApp. WhatsApp is one of the best examples of message passing systems. Even Facebook falls under the same line. Emails are also way of message passing system. Characteristic of course is different, but majority of the parameters will apply to email, Facebook, WhatsApp. I'll be referring WhatsApp for continuity, and wherever I'll switch to other two applications whenever I feel it is necessary. Okay. No shared memory. Every process uses its own address space. So when you are in a WhatsApp group, all the time mailbox lies on your smartphone and you are using your own address space. Communication link is necessary between the processes. Obviously, right? For our WhatsApp to work, you have to be on the net, which provides you the communication link. This is useful in distributed environment where sender and receiver or senders and receivers are placed at geographically different locations. That is the distributed environment. So this is really useful there. This uses send-receive mechanism. When we are discussing all this, in the mind always run WhatsApp. What happens on WhatsApp? So this uses send-receive mechanism. Messages can be of fixed size. For example, a packet which we send by post office, or of variable size. For example, email, WhatsApp messages. The messages can be of variable sizes. Now several methods are available for logical implementations. We can have a direct or indirect communication. We can have synchronous or asynchronous communication. We can have automatic or explicit buffering. And also possible are various combinations of these logical implementations. Let's see one by one. Issues related with logical implementations. There are certain issues, of course. Naming. Processes must have a way to refer to each other. So how does one process refer to the other process? That's the naming issue. Direct communication. This is typically symmetric because each sender explicitly name the recipient. indirect communication which is symmetric. For example, the send will say, send this message to process P. Recipient is explicitly mentioned here, indirect communication, and this is symmetric communication. Also is receive. It says that receive a message from process which is Q. So who is supposed to send, whom to send, from whom to receive, explicitly mentioned in send and receive. This communication link has certain properties. Link is established automatically because P is there, sender is Q. So between P and Q the link gets established automatically. Link is associated with exactly two processes because there can be only one name mentioned here. Between each pair of processes there exists exactly one link. So there are not multiple paths among the two processes. Now direct communication asymmetric. Just now we covered direct communication symmetric. Now we are going for direct communication asymmetric. So what happens here is only sender process explicitly name the recipient. Receiver need not name the sender. Alright. So there are multiple recipients and only one sender. So out of number of recipients, which recipient exactly to receive the message is to be mentioned by sender. However, since there is only one sender among all, every receiver knows that if at all a message has to come, it has to come only from one sender whose name is already known. So receiver need not name the sender. Message is something, format is send P message, send the message to process P. While receiving, receive the message from any process, variable ID. So open to all. Disadvantages of direct communication. This is the limited modularity of the resulting process definition. How you are going to force, how you are going to identify. Naming becomes really difficult because there are so many receivers and sender. There might be more than one sender. So the issue might be complicated here. Change of name of a process calls for changing all other process definition. One process changes the name in the network and all other processes must know the change. They must change in their code. Indirect communication. Messages are sent to or received from mailboxes or ports, typically mailboxes. Mailbox abstract view, an object where messages can be placed or removed. So somebody can push in messages in the mailbox and somebody can remove messages. Two processes can communicate only if they have a shared mailbox. That's not true. Send a message. Send message to mailbox A. Receive a message from mailbox A. Remember that now what is mentioned here is the ID of the mailbox and not the process. Alright. Consider processes P1, P2 and P3 are sharing a mailbox. An issue is discussed now here. P1 sends a message to the mailbox and both P2 and P3 execute receive. So one message has arrived in the mailbox, both P2 and P3 has executed receive, so both are claiming the same message. The question is, which one of P2 or P3 will receive message? There are three possibilities. Allow a mailbox to be associated between two processes only. But then the moment you do this, this becomes a direct communication. So scrap this possibility. This is not allowed. Next, allow at most one process to execute receive at a time. Fine, this can be done. So only one process is executing receive. Only one process is allowed to receive the message. Other receive by other process fails. Or as soon as the message comes, if more than one process is execute receive, choose one of the P2 or P3 randomly and send the message. But then there is no logic in this. This probably is going to work more. Number 2. Mailbox may be owned by either by a process or operating system. Two possibilities. Mailbox creation is done by operating system, but it can be possessed by a process. For example, you can create a WhatsApp group. So WhatsApp is allowing to create the group, but you are the owner of that. That is admin. The process owns a mailbox. Mailbox is part of process address space. Processes recognized as owner process can only receive messages and user process can only send messages. So creator, who is the owner, can only receive messages and all other processes can only send messages. So this is a one-way communication kind of stuff. Mailbox disappears when owner process terminates. Operating system own mailbox. Now, owner of the mailbox is operating system. Mailbox is independent and not attached to any process. Operating system provides following mechanism. It provides you other things. Create a mailbox, send to or receive messages from mailbox, delete a mailbox. Always compare these mailboxes with WhatsApp groups and now think whether WhatsApp group mailbox or group is process owned or operating system owned. That is, who is the owner, WhatsApp or you, if you have created the group. Now when more than one processes are working, some kind of synchronization is necessary. There are two types of synchronous achievement synchronous possibilities. One is blocking, another is non-blocking. Blocking is synchronous, non-blocking is asynchronous. So accordingly, you have blocking send, blocking receive, and you have non-blocking send and non-blocking receive. Blocking send, sender is blocked until the message is received by recipient or mailbox. And blocking receive, the recipient is blocked until message is received. For example, here, presume that you are making a call on your cell phone. Now you are blocked until the message, the call has been picked up by the person whom you are calling, the callee. Of course, there is time limit is there. If the receiver does not respond within specified amount of time, the call gets cut. So that's a time bound that is attached, but it's a blocking send. Non-blocking send, sender sends message and resumes its execution. Something like you are sending a message on a WhatsApp group and you need not wait until it has been received by all members of the group. You simply send it and resume your own work. Non-blocking receive, the receiver retrieves either a message or null. So if there is a message in the mailbox, receiver will receive it, or it will receive an indication that there is nothing in the mailbox. Buffering. You need buffering whenever there is communication happens, but buffering may be provided, may not be provided. Whether communication is direct or indirect, messages exchanged by processes reside in temporary queue. There are three ways of queue implementations. Number one, zero capacity. Queue cannot hold any messages. Obviously, the capacity is zero. So, if receiver is not ready, then sender is blocked. If there is no buffer, by default it becomes synchronous blocked. Bounded capacity. Queue has limited capacity to store messages. Sender may be blocked if queue is full. Receiver may be blocked if queue is empty. So normal conditions will come into play now. And this is what is the most practical thing that happens. Unbounded capacity. Queue has infinite capacity. The sender is never blocked. However, receiver may block if queue is empty. However, since there is infinite capacity of the buffer, sender will never get blocked. Okay, let's move on to the next point, 2.6, scheduling criteria. So for any scheduling algorithm, what is the criteria? CPU utilization. Aim of scheduling algorithm is to keep the CPU as busy as possible. Throughput. Number of processes that complete their execution per unit of time is the definition of throughput. Throughput means number of processes completed per unit of time. Turnaround time. Amount of time to execute a particular process. So from the time process is submitted to the system till the process is completed, total time is said to be turnaround time. Waiting time. Amount of time a process has been waiting in the ready queue. Okay. Amount of time a process has been waiting in the ready queue. Response time. Amount of time it takes from when a request was submitted until the first response is produced. Okay, first response, nothing like turnaround time. This obviously will be bigger than waiting time. Scheduling algorithm optimization criteria. 1. Different criteria. Max CPU utilization. So the algorithm will be better if it increases the CPU utilization. Max possible is 100%. Number 2, max throughput. Throughput, number of processes completed in a unit of time, in particular unit of time. So this number of processes should be higher and higher, that is preferred. Turnaround time, minimum. Remember that this max throughput and minimum turnaround time are actually related with each other and inversely proportional. More is the throughput, lesser is the turnaround time. Waiting time for a process should be minimal. Can the algorithm reduce waiting time for a process or for a process in general that is submitted for execution in the system? Minimum response time. Earlier response from the system for a process, better is the feeling. So response time has to be as minimal as possible. So these are the criteria basically for scheduling algorithms. Now actually scheduling algorithms. what they do. These scheduling algorithms deals with selecting a process from ready queue or ready list for CPU allocation. Remember the straight transition diagram of a process from ready to running, running to ready. Okay. So there are more than one processes in the ready list, and scheduling algorithm is picking up one of the processes and allocating it the CPU. Many different CPU scheduling algorithms are available. We will be studying them one by one. Let's see first. The simplest one may not be the best. First come first served, FCFS scheduling. Processes are listed here and burst time is listed here. So this burst time is amount of CPU time they need to complete their execution. P1 says 24 units of time, P2 and P3 says 3 each. Also suppose that processes arrive in the order P1, P2, P3. Might be at the same amount of time or same unit of time. But then still the order says first P1, then P2, then P3. So what will happen actually is, since P1 has come first, CPU is available, P1 will get the control of CPU immediately. And once it gets the CPU control, it will continue for the required burst time, which is 24. So 0 to 24, P1 will have control over CPU. Once P1 completes, then P2 will get done, and from 24 to 27, P2 will have control of CPU because its burst time is 3. Then P3 will have control of CPU, which again says burst time of 3, and from 27 to 30, P3 will be there. Now let us calculate waiting time for P1, P2 and P3. For P1, there was no waiting time, 0. But for P2, it had to wait 24 units of time for its execution to begin. So waiting time for P2 is 24. Going with the same logic, for P3, it is 30 units of time, 27 units of time. So 0, 24 and 27. By the way, this kind of figure is called as Gantt chart. Okay. Now average waiting time will be sum of these three divided by 3. 0 plus 24 plus 27 divided by 3 gives us 17. Okay. Let's move on. Suppose that the processes arrive in the order P2, P3 and then P1. The Gantt chart for the schedule is as follows. Now the best thing is, pause the video, take down the burst times of P1, P2, P3, draw the Gantt chart and then come back. Check whether you are correct or not. The Gantt chart has to be like this. First P2, then P3, then P1. P2, 0 to 3, P3, 3 to 6, and 6 to 30, P1. Okay. Now what happens is, what is the waiting time for P1, P2 and P3? Waiting time for P1 is 6 units of time. For P2 it is 0. For P3 it is 3. So 6 plus 0 plus 3 divided by 3 equal to 3. Surprisingly, remember that when the Gantt chart showed the order as P1, then P2, then P3, the average waiting time was 27, so obviously it was much higher. And here average waiting time is very less as compared to the previous, where the order is P2, then P3 and then P1. Now this effect is called as convoy effect. Short process behind long process. Whenever you have a short process behind a long process, that is P1 first and then P2 and P3, you will find the effect of called as convoy effect. And this effect should always be avoided. Yeah. So the problem that we found in the earlier example was when we scheduled a process which was asking for minimum amount of CPU time. If you schedule that first, then obviously the average turnaround time increases and the algorithm gives us a better output. So from that, another scheduling algorithm came into picture. See, throughout what will happen is we'll be discussing one algorithm, then we will find problem in that, and then we'll come out with another algorithm. So we found a problem in the previous algorithm, and then now we say that let's try to resolve that. So what we in the previous example what we found is that if we schedule first the shortest job, then the algorithm is giving us the better efficiency. So from that what came up is let us schedule first the shortest job. So the name of the algorithm is shortest job first. Do remember that this is not the ultimate scheduling algorithm, because once after discussion of this we'll find out what are the difficulties in it and we'll try to resolve coming out with different algorithms and the process will continue. So associate with each process the length of its next CPU burst. Use these lengths to schedule the process with the shortest time. This SJF algorithm is optimal, that means it gives the best average waiting time which is minimum for a given set of processes. Our difficulty, how to know length of next CPU burst. How do we know that so and so process needs CPU time for so much of time? That's the problem. But let's understand the algorithm first and then we'll go get into the problem and then we'll try to resolve the problem or the difficulty. So here is an example. Now what I would strongly recommend is open notebook, pen and start calculating the time on your own or start drawing the Gantt chart on your own. Thereby you will get the average time. Okay. So for this example we have 4 processes. Burst time is given 6 at 7 3. Arrival time is 0, that means every process is submitted to the system at the same time. In other words, these are the 4 processes in the ready list. And the algorithm is supposed to select one of them, one after another for CPU allocation. Now, if we look at the burst time, we find that P4 has the list, then is P1, then is P3, then is P2. So obviously, according to the algorithm, shortage of first, the CPU will be allocated to P4 first. When it is done with it, then there will be only 3 processes remaining with 6 at 7 as the requirement. So 6 being minimum, P1 will be scheduled. Once P1 is complete, only 2 processes P2 and P3 will remain in the system with 8 and 7 as their CPU burst time. 7 being less than 8, P3 will be scheduled and finally P2 will be scheduled. This is the scheduling. P4 first, then P1, then P3 and then P2, right? So if we draw the Gantt chart, what it shows is that waiting time for P4 is 0, for P1 is 3, for P3 is 9, for P2 is 16. So if we calculate average waiting time, P1 3, P2 16, P3 9, P4 0. So if we find out average of all these four, we get it as 7. Do you remember that SGF always gives you the minimum average waiting time? But the problem is, how do we determine length of the CPU burst? Or it's modified a bit other way, next CPU burst. The importance of this next will come later. But again, don't forget, keep your notebook open, pen ready, try to draw Gantt chart yourself or try to schedule the processes yourself once you understand the basic logic. So, determining length of next CPU burst is the problem. One solution is ask the user, the programmer, the user who is submitting the process, ask the programmer or the user, hey, what will be the CPU time that your process will need? Now, of course, that's a funny question because usually you cannot ask such a question because the user may not be maybe non-technical person, he just want to run a process and we cannot dwell him into the technicalities. It is not possible for every user also. And even if it is possible, it is not possible because even if the user is technical, it is not possible because for an interactive program, how much time the process will take ultimately is not known. So as per the course of execution, what can be guessed at the max is next. But then asking every time the user now how much is a problem. And the system will spend lot of time in asking the user now how much. So that is not really the solution, ask the user. The only solution is automatic. Now this can be done by using the length of previous CPU burst. Now this data is available with the operating system. Last time the process used so much of CPU time when it was run. No guarantee that in this run the process will need the same amount of time. But yes, the OS does have some history. Last time how much it has used. And there is one version called as preemptive version which is called as shortest remaining time first. So it's not shortage of first now, it is shortest remaining time first. Now what do you mean by this? We'll see. Let's consider an example. Now we are adding the concept of varying arrival time, which is practical. All processes need not come in the system at the same time, they might come at different times. And now system is recording their arrival time also along with the burst time. So P1 has arrived at 0, burst time is 8, P2 at 1, burst time is 6, and so on for P3 and P4. Now how the Gantt chart will look. At time 0, remember that there is only one process in the system. So at time 0, there is only one process, P1 in the system. Obviously P1 will get scheduled. Now here for this example, we are considering every time CPU is assigned for 1 unit of time for the process and the scenario is rechecked. Okay, the scenario is rechecked after every 1 unit of time. So at 0, what is the situation? Only P1 is there. No other competing process is there. Now, irrespective of looking at its burst time, P1 will be scheduled. So P1 is scheduled. And for one unit of time, P1 is not disturbed. So P1 continues to use CPU for 1 unit of time. Okay. After 1 unit of time, what is the scenario? The scenario is after 1 unit of time, P1 has used CPU time of 1. So its next CPU burst will be 8 minus 1 equal to 7. P2 now has come into the system. Its burst time is 6. P3 and P4 are yet to arrive. So the scenario is P1 7, P2 6 at 1 unit of time. Okay. So obviously, since shortest remaining time first, according to this algorithm, P2 with 6 will be scheduled onto the CPU. And P2 will continue to use it for 1 unit of time. At this juncture of time, again the scenario is reviewed by operating system. Now the scenario is P1 7, P2 5, P3 4. Are you getting it? Initially 8 has been decreased by 1 for P1. After this, since the usage of CPU by P2 in this time period, 6 has been decreased by 1 further. So it has become 5. So now the scenario is 7, 5 and 4. Shortest among these three at this juncture of time is P3. So P3 will be scheduled. It will continue to use the CPU for 1 unit of time. Situation is reviewed after at time equal to 3. At time equal to 3, the scenario is P1 7, P2 5, P3 3 now, P4 2, because P4 also is now in the race after 3 units of time. Okay. Now since after P3 the scenario is not changing, the shortest remaining time first algorithm jumps to shortest job first, obviously. So there is no new competitors coming in the system. So P4 is scheduled. After 1 unit of time, the situation can be reviewed, at which time it will be 7, 5, 3 and 1. P4 still remains the shortest, so it is rescheduled or it continues to run for another unit of time, and after that it says I am done. It goes out of the system. So at t equal to 5, the scenario is P4 has come and gone, P1, P2 and P3 are there with 7, 5 and 3, and obviously P3 will get scheduled. No further competition. Values for P1 and P2 are not changing. So for next 4 units there will not be, 3 units of time there will not be any competitor for P3. So for next 3 units of time P3 will continue to run, utilize it, its burst time will become 0, and now at t equal to 8, the scenario is P3 and P4 are out of the system, only 2 processes are remaining, P1 and P2 with 7 and 5. And again no new competitors are coming in. So P2 will continue to remain the shortest job or shortest remaining time process, and it will run for 5 continuous units, and at t equal to 13 it will go out of the system, because at this time its burst time has become 0. And now there is only one process with 7 units of requirement. There is no competitor. P1 will continue to run from 13 to 20. Okay, let's calculate now. For P1 1 to 13. Here it is 0. So if we calculate only for P1, then 0 and 12 equal to 12. So for P1 it is 12. For P2 it was 0 here. Do remember that arrival time of P2 was 1. As soon as it came, it was scheduled. So here for this time P2 it was 0, and then it had to wait for from 2 to 8. So 8 minus 2 is 6. And similarly waiting time for other two processes are calculated, and this average comes out to be 12 plus 6 plus 2 divided by 4, that is 20 by 4, which is 5. Okay. So far so good. Now the question arises, you might have more than one processes. One might say I need 8, another might say 4, third might say 2. But then usually we find that there is what is called as an priority associated importance of that process. If the importance is higher, the process should get access of CPU early. So that is what happens practically in every system. A priority number is associated with each processor. Processes are divided into number of categories, which are called as priorities. And what is the priority of that process? For that, a number is associated. Importantly, smallest integer or the smallest number indicates highest priority. So lower is the number, higher is the priority. Okay. Now in this priority scheduling, there are two ways of implementing. One is preemptive, another is non-preemptive. What is a non-preemptive? Once a CPU is allocated to the process, unless and until it says I am done, the process doesn't move. The CPU is not taken from that process. Preemptive, operating system takes the control back from a process even though the process is saying that I am not done. Problem, starvation. Are you understanding one thing? We are discussing an algorithm, we are finding a problem in it, then we are trying to find solution in the problem. So we come out with different algorithm. Even with different algorithm, the next generation of algorithm, we are finding problem, and then we'll find out the solution to that. So same way the things will move. Now the thing is, priority is constant for a process, not going to change in its lifetime. And now presume that there is always at least one process with higher priority than other processes. Are you getting it? There is at least one process in the system with higher priority than the other processes which are waiting for CPU. If this is the scenario, then and the policy simply says that always schedule highest priority process, and the process with lower priority is always finding some process in the system with higher priority. And with this scenario now, the process with lower priority will never get access to CPU. It will never be run. It will be starved out of the CPU time. So that is the problem with fixed priority, which is called as starvation. Low priority processes may never get to execute, may never get access to CPU, and that's the problem. Solution now. So we found a problem. What is the solution? Recall the sentence. This scenario, starvation, is occurring because the priorities are fixed. That's why A low priority process will always remain low priority. It can never become high priority process. So how about a dynamic priority? A dynamic priority is called as aging. And what aging does? As time progresses, increase priority of the process. So for certain units of time, if the process is waiting for CPU, increase its priority by 1. Keep it at the next level. So now lowest priority process gets up by 1 level after some waiting time period to the next higher priority level after further waiting. And with this methodology, the lowest priority process eventually, after maybe with a longer waiting time, will reach to the highest priority level, and it will get access to the CPU. So CPU will not be denied to lowest priority process forever. Maybe it has to wait for a longer amount of time, but still, now this aging factor, if we add, it will ensure that a lowest priority process also is getting the access to CPU. Now this is an example of priority scheduling. CPU times are given, priorities are given. Right now this is fixed priority. And if you look at the priorities, remember that this is number associated for the priority. Lowest the number, higher the priority. Lowest the number, highest the priority. Okay. So if you look at, this is 1, then 2, then 3, then 4, then 5. Do remember that we are not now looking at the burst time. We are looking at the priority first. Okay. And this tells us that P2 should be scheduled first, then P5, then P1, then P3, and then P4. This is the Gantt chart presuming that every process is in the system, has been submitted in the system at t equal to 0. All processes have come at the same time. So now it becomes very simple. Instead of shortage of first, highest priority first is the algorithm. And then how much CPU time it uses is mentioned here, but the scheduling is done based on the priority. So accordingly you are finding that P2 is scheduled first, then is P5 with 2, then is P1 with 3, then is P3 with 4, and then is P4 with 5. This 1, 2, 3, 4, 5 I have talked about the priority level. However, whenever the process gets access to the CPU, it uses the CPU for its burst time. Alright? And from the Gantt chart, we find out that average waiting time equal to 8.2 milliseconds, presuming that burst time is in milliseconds. I am leaving this simple calculation to you only. Hopefully you have a notebook and pen ready. Great. Let's go back a bit. Study this further, this table itself. What we observed here is, for any priority there is only one process, right? On priority level 1 there is only one process, on 2 there is only one process, and so on. Now the question is, what if we have more than one processes with the same priority? This can very well happen in a system which is running hundreds of processes simultaneously. You cannot have hundreds or thousands of priority levels. Priority levels are typically very limited numbers. So it is just possible that you might have more than one prior processes with the same priority number. Now, if that is the case, what are you going to do? I mean, if P4 also has priority 1, if P1 also has priority 1, so there are three processes with same priority, what are you going to do? Which is a practical scenario. Now, in this case, the approach taken is different, which is called as a round robin. Now let's go through this. If you understand these points, okay. No, doesn't matter. With examples, the things will be very clear. But for the sake of reading, I am reading now. Each process gets a small unit of CPU time, which is called as time quantum, denoted by Q, usually 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added to the end of the ready queue. If there are n processes in the ready queue and the time quantum is Q, then each process gets 1 by n of the CPU time in chunks of at most Q time units at one time. No process waits more than n minus 1 star Q time units. Good. My advice is, we'll proceed. We'll check with examples. Once you understand the examples, come back, read these points, you will understand them. Timer interrupts every quantum to schedule next process. Performance is, if Q is large, then the performance is like first in, first out, the very first algorithm that we discussed. If Q is small, then there is another problem. Q must be large with respect to context switch, otherwise overhead is too high. This simply means that if Q is too large, you will lose the advantage. If Q is too small, you will lose the advantage. So output is same. What these 2 points mean to say is that Q should be optimum. Now, how to calculate that optimum? We will also see that. So, example of RR with time quantum equal to 4. You can check these things with different time quantums. For example, I would recommend 2 for the same scenario. So here what is happening is, three processes competing with each other for CPU time. Their burst times are 24:33. All have come at the same time, that is arrival time is 0. Now which process will be scheduled? There is no priority, indicating that all three processes are at the same priority. So which one will you select? How the queue will look like? Recall that it's a ready list. The head is pointing to first process in the list and the tail is pointing to the last. So this is a singly linked list, P1 to P2 to P3, and there is head and tail. Head is pointing to P1 and tail is pointing to P3. Got it? Okay. Now what the algorithm does is, it picks up the process which is pointed to by head. Right now head is pointing to P1 and CPU gets allocated to P1. But now for how much time? For 4 units of time. Situation then is reviewed after every 4 units of time. Let's see the Gantt chart. So at 0, P1 is scheduled, uses the CPU for 4 units of time. Remember that in shortest remaining time we recalculated situation after every 1 unit of time. It is recalculated after time quantum, which is 4, that is Q. So after 4 units of time, the scenario will be P1 20, P2 3, P3 3. But importantly, now what the algorithm does is, it pushes P1 back at the end. So now head is pointing to P2 and tail is pointing to P1, which is last now. That is why it is called as round robin. Okay. and then P2 will get scheduled for 4 units of time. But then P2 says I am done with 3. So from 4 to 7, P2 will go out of the system. Since P2 has gone out of the system, now head will point to P3, tail is still point to P1. P3 will be picked, allocated to the CPU. Though the time quantum is 4, it says I need only for 3 units of time, so it will use for 3 units of time, it will go out of the system. And the usual thing, no burst time, nothing is to be seen, there is no competitor for P1. For next 20 units of time, P1 will keep on using the CPU, and after that it will be done. It will also go out of the system. Typically, there are few codes. Typically, higher average turnaround time than SJF, shortage job first, but response for every process is better. If we compare SJF and this algorithm, there is no problem. Even now, knowing the burst time is not necessarily. Just put the first in the sequence, assign CPU burst for the time quantum. If the process wish to come back to ready list, push it at the end. As simple as that. The operating system does not need any additional information. But this results in a higher average turnaround time as compared with SJF, but response is better. Q should be large compared to context switch time. We recall context switch time we discussed at the beginning of the chapter. One process is taken out from running, pushed into the ready, another process is loaded onto the CPU from ready to running. So context of one process is saved, another process is loaded. That is called as the context switch time. And this context switch time usually should be less than the context switch time. So Q usually is from 10 millisecond to 100 millisecond. This is the operating system designer's choice. And the context switch usually takes less than 10 milliseconds. That is what practically majority of the operating systems uses. Time quantum and context switch time. We have a process time, quantum and context switches. So for a time quantum, for the same process, does it need context switch? If yes, how many? That depends on the time quantum. So process time, burst time is 10 fixed. Now what varies is quantum. The Q equal to 12, then obviously once CPU time is given to this process, it will complete and go out. So it won't need any context switch in its lifetime. The time quantum is 6. Then for the first run, it will use CPU for 6 units of time. 10 minus 6, 4 will remain. And in the next round, it will get those 10. Those remaining 4. And thereby completing 10. So in the lifetime of the process, for 10 units of time, there is one context switch, right? Now, if the time quantum is decreased further to 1, the number of context switches for the same process will be 9, because it is given access to the CPU only for 1 unit of time at a time. So after every 1 unit of time, if there is another competing process, a context switch will take place. This is turnaround time, graph of turnaround time, average turnaround time versus time quantum. So the algorithm performance that will differ with time quantum. And you'll remember that for basically this performance is average turnaround time is increasing here, then decreasing here, increasing drastically here from when it shifted from 3 to 5, then from it comes down to 10.5, stays there for 6 and 7 also. Now all this you can do for this. Presume time quantum 1, apply the round robin algorithm, find out how many total context switches are there, map them. For do same thing with 2, do same thing with 3, you will get these values yourself. Okay, do it like what we have done, except that first P1 for 1 unit of time, then it will remain 5, head will point to P2 and tail will point to P1, and like that proceed and calculate how many switches are taken or what is the average turnaround time for various time quantums. The general observation says that 80% of CPU burst should be shorter than Q. Then only you get a better turnaround time. Multi-level queue. Ready queue is partitioned into separate queues. Remember that we discussed that there might be processes with different priority. We are continuing with that now. Typically, the processes which are interactive, where the user is sitting in front of the computer and waiting for some response from the system, these processes are run in foreground, and where the user has submitted the system, gone, is going to take ready to wait for longer amount of time, those are run in background. Typically the batch processes. In this case, the process permanently remains in that queue. Each queue has its own scheduling algorithm. So the scheduling algorithm varies as per the queue. Foreground processes, round robin. Background processes, first come first served. Scheduling must be done between the queues. What for we do this? Because if this is not done, if we go ahead with fixed priority scheduling, as discussed earlier, there is the possibility of starvation. The process in the lower priority level will never get access to CPU. So better go for some other solution between the queues. Remember that now we are discussing between the queues, not between the processes. Time slice. Each queue gets a certain amount of CPU time which it can schedule amongst its processes. Usually 80% of CPU time is allocated for processes in round robin, for the foreground in round robin, and 20% of CPU time is allocated for background processes which are basically scheduled according to the first come first served basis algorithm. Usually highest priority are the system processes, then one step low is interactive processes, one step low is interactive editing processes where somebody is using something like Word, etc., etc. Then is the batch processes, and I don't know why student processes has come, because these are typically not categorized as per user, because in certain cases a student might submit a process that is interactive, and obviously it has to go at this priority level. Anyway, rather than student, read it as lowest priority processes. And we have different queues and different scheduling algorithms are coming into play. multi-level feedback queue. Let us begin now the multi-level feedback queue, probably the last leg of the unit. As the name suggests, multi-level. We have different levels of queues. For certain reason, they are also called as feedback. We'll see how do they provide the feedback. Now here, a process can move between various queues. Aging can be implemented this way. Okay. Remember, some time back we thought of starvation and then aging of the processes and then shifting them from one queue or lower priority queue to higher priority queue. Now this multi-level feedback queue scheduler is defined by the following parameters. So the multi-level feedback queue has to have following parameters, or it should implement following parameters. Number one, as the name suggests, it should have a number of queues. Every queue should have its own scheduling algorithm. Remember that the scheduling algorithm may differ from queue to queue. Then method used to determine when to upgrade a process. So when to apply aging factor to a process, when to move the process from lower priority to higher priority queue. Also it needs to have method to determine when to demote a process. This is opposite of upgrading. So process may be brought from higher to lower priority queue. Method used to determine which queue a process will enter when that process needs service. So which process to go in which queue, there also should be a method to determine this. This is an example of a multi-level feedback queue. Here there are three queues. They are named as Q0, Q1 and Q2. Okay. Now for Q0, RR, the round robin scheduling algorithm is used. For Q1 also round robin algorithm is used. And for Q2, first come first served, FCFS algorithm is used. Now between Q0 and Q1, they differ in the time quantum that is allowed. So in Q0 the time quantum is 8 units, Q1 the time quantum is 16 units, and in Q2 there is no concept of time quantum. A process once gets the CPU, completes it, and then only returns back the CPU. FCFS. Okay. So three queues, Q0, Q1, Q2. Q0, Q1 imply RR as the scheduling algorithm with different time quantums of 8 and 16, and Q2 employs FCFS. Now how exactly the scheduling occurs. A process usually always enters time quantum 8, that is Q0. A new job enters Q0 which is served RR with time quantum 8. Right? Obviously Q0 is providing time quantum of 8. Every new process enters in this. Now what can happen within this time quantum 8? The process may complete and go out of the system, or the process is yet to be complete but the time quantum has finished. Now the moment this happens for a process, the process is moved on to the Q1. So when process gains CPU, job receives 8 milliseconds or whatever is the time quantum. If it does not finish in 8 milliseconds, job is moved to Q1 with time quantum of 16. So job is moved to Q1. Now what happens in Q1? At Q1, job is again served in round robin fashion. But now the time quantum is 16 units of time, and it is now getting additional 16 minutes. This addition is to previous 8. Now two things can happen. One, the process might complete its execution and then moves out of the system. If it does not happen, then the process is moved to Q2, which provides FCFS. And what happens in FCFS? CPU access is given to the process. Now the process is not preempted. It completes its execution and then only returns back the CPU. So at Q1, job is again served round robin and receives 16 additional milliseconds. If it still does not complete, it is preempted and moved to Q2. Remember that preemption is not there in Q2. Okay, this is our multi-level feedback queue works. Why it is called as feedback? Because the process is giving feedback that I am done or I am not done, and that I am not done is being used by to shift the process from Q0 to Q1 or Q1 to Q2. Up till now, all examples where we are thinking about there is only one CPU. And then there are systems where more than one processors are available, more than one CPUs are available. And now the question comes is, if the system have more than one processor, how the scheduling is taking place? Now, such systems are called as systematic processing, also denoted as SMP. SMP is used for multiple processor scheduling. SMP involves a multiprocessor computer hardware. Obviously, the computer hardware now has more than one processor, and of course supporting software architecture where two or more identical processors are connected to a single shared main memory. We'll be going in the architectural details probably on the next slide. So hold on if there are any questions about this point. SMP systems are tightly coupled multiprocessor systems with a pool of homogeneous processors running independent of each other. Okay. So all are homogeneous processors. A processor is for its running is not dependent on other processor. Every processor is independent in its working fashion. A process can be scheduled on any processor for execution. So given a process, the situation is it can be put onto any process. But there are certain processes which says that no, I want only this specific CPU. Are you getting it? This line says that a process can be scheduled onto any processor, but there might be few processes which has a peculiar characteristics by which they are almost saying that no, any processor won't work for me, only this processor or this subset of the processors are okay for me. That is called as processor affinity or CPU pinning. So a process is getting pinned to a CPU. This enables the binding and unbinding of a process to a range of processors. This range of processors might include 1, 2, as many as the system have, so that the process will execute only on the designated range of processors. So the processors are getting pinned to a subset of the processors. That is called as CPU pinning or processor affinity. Now how does the architecture, SMP architecture looks? Few things that have been said. It's a tightly coupled. Now see what is there. This is the common system bus available for everybody. Whether you are a processor or I/O or main memory, this is the common processor. Sorry, common system bus. Data is put onto system bus or given or taken out from the system bus, maybe by main memory or a processor or I/O device. Now, when particular data is kept on this, who is supposed to receive it, whether the processor 1, 2, 3, N or I/O. Now, this is taken care by what is called as the bus arbiter. This bus arbiter takes care that whatever data is put on the common bus goes to the respective recipient. Alright? So, either it might go to processor 1 or 2 or N or I/O. Now, it can be suffice if you don't show the cache. But this is what usually happens. From system bus data is first pushed to cache and then on to the processor, which processor always pulls data from its own cache. Okay? Now, why this system is called as tightly coupled? Because all processors or all I/O devices are using same main memory and they are all connected to a common system bus. This also means that they have to be part of a single system. They are not part of different systems which are kept at geographical different locations. That is why this is called as tightly coupled system. There is another kind of scheduling, real-time scheduling. Now, in this real-time scheduling there are two types. One soft real-time, another hard real-time. As the name suggests, soft real-time is let's try to run a process into real-time is basically the interest in soft real-time. And when we say that no, this process has to be run in the real time, there is no other go, then the system is called as hard real-time system. So soft real-time systems, there is no guarantee as to when critical real-time process will be scheduled. Right? So whether real-time is really achieved or not, can't say. But yes, efforts are there to go for real-time. That is why this is called as soft. Hard real-time systems, here it says must. Task must be serviced by its deadline. There is no other go, there is no excuse. And such systems are called as hard real-time systems. So for example, if you think about a satellite launching operation or a missile launching operation, all has to be hard real-time systems. Now, there are few terminologies coming into play: interrupt latency and dispatch latency. Let's see the figure. At the bottom what we have is a timeline. So time flows from left to right. Task T is running. So any process is running at present onto the CPU. And now what happens is an interrupt arrives, which is at the higher priority level than task T. The obvious action is to suspend task T, give control to interrupt, and when interrupt is complete, reload the task. This is called as preemption, obviously. Now, when an interrupt arrives, certain time is taken for the process switch. When an interrupt arrives, first determine interrupt type, which kind of interrupt it is. Okay. If it is higher interrupt, higher priority interrupt, then it has to be serviced immediately, otherwise the interrupt can wait. But let's presume that it is higher level. This is higher priority interrupt, so this has to be serviced immediately. So currently executing task has to be preempted, and the context switch now should take place. That is, T goes out, interrupt service routine ISR will come in. This will take certain amount of time, and then ISR will begin its execution. ISR is interrupt service routine. These are typically short ones, but still a context switch is necessary and ISR execution does take some time. Now from the time interrupt has arrived till the time of beginning of execution of ISR is called as interrupt latency. Alright? From the time interrupt has arrived till its ISR execution begins is called as interrupt latency. So interrupt latency, time from arrival of interrupt to start of routine that services interrupt. That is to start of ISR. Dispatch latency, time for schedule to take current process off CPU and switch to another. So this is dispatch latency. This time is necessary for a context switch, and both these together will give us the total time, that is from the moment interrupt has arrived till the ISR is service, another context switch is there, and then the interrupted process is re-begins its execution. So there is another context switch here from interrupt to process, and then the interrupted process will restart its execution. But dispatch latency is this total, sorry, this is interrupt latency, and dispatch latency is typically this. Okay. Now conflict phase of dispatch latency is another terminology. Now what is conflict? The question is it necessary that a process must always be forced to preempt only on arrival of interrupt? Well, not necessarily. It might happen that a process is running. In its lifetime, it keeps on requesting different resources, holds the resources until it is done with the resource usage, and then returns back the resources to the system. Okay. Now consider a situation: a process is there, it has requested a resource from the system has allocated it, it has partially used it. By holding the resource still with it, the process has gone into the ready list. Okay. Now another process is scheduled. The process says that I want a resource which is currently held by another process, and the situation is that the process which is asking is at the higher priority than the process which is currently holding the resource. Now there comes a what is called as conflict. And what the system does? It obviously favors the high priority process. It takes away the allocated resource from the low priority process and assigns it to the higher priority requesting process. Now this is called as conflict phase. Preemption of any process running in kernel mode. So any process in kernel mode also it is preempted. Second, release of resources by low priority process needed by high priority processes. Right? So that is what is called as conflict phase. Now what do you mean by conflict phase dispatch latency? As this is the timeline, left to right. Remember that now what has happened? An event has occurred. That is, an interrupt has come. As seen previously, interrupt is processed. The process is made available. Because of conflict now, what is happening? Resource is taken out and given to other process. So whether there is any conflict or not is resolved here. If the conflict is there, resource is taken out from one process to and given to another process. This is the dispatch time. The total time of conflict and dispatch is dispatch latency. And then the real-time processing execution begins. You getting the thing? An interrupt has come. It is serviced. The interrupt now says that currently holding resource by a low priority process is needed by the high priority process. So it finds out that there is a conflict. Then it resolves that conflict, that is by taking out resource from low priority and assigning it to higher priority. This is the dispatch latency, and then the real-time process execution begins, and the real-time process execution ends here. Okay, this is the timeline for that at this moment of time. So from the time the interrupt has occurred till this interrupted process re-begins its execution, this is called as response interval. Okay, are the things clear to you now? Everything what is mentioned here on the slide? Okay, let's move on. Priority based real-time scheduling. We are now not only discussing real-time, but in real-time we are discussing priority. So priority among the real-time processes. For real-time scheduling, scheduler must support preemptive, obviously, priority-based scheduling. This guarantees only soft real-time, as we discussed earlier. For hard real-time, must also provide ability to meet deadlines. So, what is hard real-time? The process is that come what may, me or myself, I should be able to complete within this specified duration of time. That's it. That means I want a real-time system. This is called as hard real-time system. So it gives you the deadline also. U means to the system. Processes have new characteristics. These are called as periodic ones, require CPU at constant interval. So there are certain processes which will keep on saying that I need CPU for this period, and this is repeatedly happening. For example, a timer interrupt in a system. It will ping the system, update the time, and come out. Probably the smallest ISR, but yes, it keeps on asking for CPU time periodically. This has processing time T, so actual processing time for the process is, or the ISR is T, deadline is D, and period is P. Now what this means is, and then 0 less or equal to T, less or equal to D, less or equal to P means we'll come to know. For to this rate also we'll come back later. Let's move on and then we'll come back. Look what is happening. There is a process which is periodically pinging for CPU time. When it is getting the time period, CPU access, it is taking this much amount of time, shown by the filled rectangle. So the moment it gets control of the CPU, it is not leaving, this is non-preemptive. It completes its task and goes out, and again comes back after certain time period. And this time period is fixed, which is indicated by P. Okay, so the process is coming back again and again demanding CPU time in particular periods. This is period 1, period 2, period 3, and it goes on like that. Whenever it is getting on to the CPU access is given, it is taking T units of time. And what it says is that, okay, the system must give me T units of CPU access within D duration. In the sense, for example, every say 100 milliseconds the process is coming back to the system asking for CPU time. And what it says is I need the CPU time for 2 milliseconds. Okay? But every 100 milliseconds, 2 milliseconds I need it. And in that period, from 0 to 30 or 0 to 10, whatever it is, period, system must give me 2 milliseconds. So P is 100, D is let's say 30, and T is 2. Are you getting it? And that is what is meant here. 0 less than T, less or equal to D, less or equal to P. 100, 30, 2, and obviously 2 is greater than 0. If T equal to 0, it really doesn't have any meaning, because T equal to 0 indicates that the process is never requiring CPU time. So I feel probably this has to be 0 less than T, and then it can be less or equal to D, less or equal to P. That is okay. And rate of periodic task is 1 upon P. That means every 100 milliseconds the process is coming back to the system and asking for CPU time. Scheduling algorithms and performance evaluation. The top line in the table shows columns are titled as short-term scheduler, long-term scheduler, and medium-term scheduler. We have seen this, right? And now the rows titles are execution time and invocation frequency. Short-term scheduler, in execution it is shortest among the three. Long-term is the highest, and in between these two lies the medium term, which is asking for a medium amount of CPU time or medium amount of execution time. So short term is shortest, long term is highest, medium term is medium. How about the frequency? In short term it is highest. So every 10 milliseconds or 20 milliseconds a process needs to be switched from running to ready or any other state. In case of long term, this is which is typically applied for batch processing. The process is submitted, the user says that in coming a day or 2 or 6 hours complete the process. I am not in a hurry. And he submits and goes back. So execution time is obviously highest and invocation frequency obviously is lowest. And in between these two, shortest and highest, or highest and lowest, lies the medium term, medium. And typically medium term scheduler is applied to swapping processes in and out. Alright. Now with this we are completing unit 2. Soon we will meet for unit number 3. Bye for now.